In this lecture, we're going to be looking at linked lists, and I'm going to do it using this file. It's called Playground, and it's in the algs13 package. When you open this file, you'll see immediately on line 5, there's a declaration of a node named first. And then on line 6, there's a declaration of a node class. The node class has two fields, item and next, and it has a constructor which accepts the item and next and assigns the parameters to the fields. When you run a program and build out the structure in memory, they're going to look like I'm showing over here on the right. What you can see is that I have two structures called list1 and list2. Those structures have a type. Each of them is a playground. So there's the class playground here. I have two instances of that type. So the variables here are called list1, pointing to this playground here, and list2, pointing to this playground here. The playgrounds each have a field called first, and you can see that on line 5. The type of first, it's a pointer to a node. The first node of the first playground is 5, which you can see here. You can see how list 1 represents the list of elements 5, 11, 5, 5, and how list 2 here represents the list 24, 35, 67. The first list has 4 nodes. Each node holds one element of data, and those elements are in the order we would expect. So first a 5, then the 11, then 2 5s. Likewise for list 2, we have 3 data items, and therefore we have 3 nodes, and they are in the order we expect, 24, 35, 67. I've marked the node class as static on line 6. In your textbook, the authors prefer not to do this. I have marked the class static because it avoids some unnecessary pointers in the pictures. To see this, let me remove the keyword static and show you what happens. So I'll remove it here. A few edits are necessary to get the code to compile once you've done that. But when you run it, what you'll find is you end up with a picture like this. So if you look at it, you can see the main program still has list 1 and list 2. In this case, the objects are called a playground with non-static node, not simply a playground. And the first is pointing to the node. Note the node always has a this $0 pointing back to the playground. And this is consistent for all of the nodes. They're all going to have a pointer back to the creating object. This is the meaning of the word static on a class. When you have a non-static class, you have a pointer to the surrounding object or the creating object. And when you have a static class, you do not have that pointer. For our nodes, we don't need to have that pointer to the outer object. And so I'm going to write the code without using that pointer. And therefore, I'll mark the code as having a static node. To see how lists are created, it's handy to use a simpler creator than the of method, which I have defined here. The of method is quite fancy. It takes a string and parses all of the numbers and creates nodes corresponding to those numbers. It's very convenient for developing tests and playing around with lists, but it's also kind of difficult to understand. So I'll start by looking at a much simpler example, which is written here. So let me just run this. The code begins at line 34 by invoking the method example. The example method takes one parameter and then starts creating nodes. On line 17, we create a node with item 11 and next equal to null. This is done by invoking the constructor, but the constructor doesn't do anything except copy its parameters into the fields. So you can see here I'm just skipping that in the display. Once I've constructed the node with item 11 and next equal to null, I'll return that back to the example and save it as in a variable called x1. So once we're done here, x1 is a pointer to a node with item 11. Then we'll repeat this with x2, having a node with item 21. x3 will have 31. x4 will have 41. So once I've created all my nodes, I can then create a playground to put them all together. So when I create a playground, I'm going to create an object that has a first field. So here's my playground. Note that first is initially null. So if you don't specify a value or a constructor, then Java will initialize the fields all to their 0 value, which is null for objects. When I return here, I now have my playground object called result, and I have 4 nodes. So what we need to do is to stitch them together. So on line 22 here, I will set the result first to be equal to x1. So that should be this node, x1, which is now result first. Note that this doesn't create a new node object. All it does is copy the reference. This is an alias. Result.first and x1 refer to the same object in memory. I'm going to do this again on line 23. I'm going to set x1.next to be equal to x2. So we're going to take the object with value 21 here and stitch it after the object with value 11. We can continue this on line 24 to take the object with item 31 and put it after the object with value 21. And finally, on line 25, we'll take the object with item 41 and put it after 31. At this point, I've actually created the correct structure. I have my playground first pointing to 11, then next to 21, next to 31, next to 41. At this point, the code can return, and I've got the list I wanted. Note that all of the temporary variables, the local variables of the example field, the parameter I, all of them are deallocated when the function returns. All of that goes away. But I'm returning the result. The result is this playground. Therefore, it and all of the objects that are reachable from it will stay alive. So they are returned as a return value. Back in main 1, I then stitch that in for my first list. Now I'm going to repeat this twice again. So I'll have another one with 15, 25, etc. Then we'll have another one with 17, 27, etc. And in the end, we have then 3 linked lists. Example 1, example 2, and example 3. Finally, on line 38, the code prints the item. And you can see it there in the console. The item it's printing is x.item, where x is example.first. So I'm going to example1.first. That is the node with item 11. And I'm then printing out 11. It's worth playing around with this and trying to print different things. So let's do some experimenting here without actually redrawing the picture. I just want to play around with the pointers. So I'm going to comment out run and run the code. And you'll see it's getting me 11. One thing to note is that I could also do example 2 here. And what I expect to get out at this point is example 2's first item, which would be 15. And indeed, that works. I could also get example 2's second item. So there's many ways to do that, but one of them is to just write next here. And now my node X is actually going to point to this item here. So if I run this, there you can see it. Here you can see in the picture that X is indeed pointing to the second node of example 2. You can play this game as much as you want. So I can go to the last element by stringing along 3 next pointers. And if I run this, I'll get a new picture here, which I can then look at. Just go to the end. And you can see indeed X is pointing to the last element. What happens if I try to set next.next again after this one? Well, I'm going to end up with a problem if I try to print out this item. So I'm not going to print out the item. I'll just print out X. But let's just see what X's value will be if I do this. And to see it, we can just look at the pictures. And you can see here X at this point is null. Well, that makes sense because X was pointing to the last item. So X next is null, and that's the value you get. If I try to dereference a null pointer, I'll get a runtime exception. And you can see that here. I'm going to get a null pointer exception on line 38. What's happening here? Well, it means that X is null. You only get a null pointer exception when something on the left-hand side of the dot operator is null. So on this line, it's really clear. There's only one dot operator, so it has to be X. And indeed, X is null. Null pointer exceptions are very similar to array index out of bounds exceptions for array-based data structures. A null pointer exception typically means you're trying to go beyond or before or somehow reference the structure in an invalid way. That's roughly how lists are created. We'll talk more about array creation next week, but for now I really want to concentrate on how you use a list that's already been created in order to compute something. And the simplest thing for us to do is to just go through the elements of a list and look at each one and then do some processing on it. So I just want to look at how you do that. So let's suppose we want to compute num5s on, let's say, the list on the left. That's 5, 11, 5, 5. Well, if we're going to be computing this, like usual, we'll start assuming that we're somewhere in the middle of the list. So let's suppose we're pointing at the second to last element. That's the second 5. So let's suppose we're here. What do I need to know? Well, clearly I need to know where I am. So we need a variable to keep track of where we are. We also need some sort of notation for keeping track of how many 5s we've seen so far. And my favorite name for those kind of things would be just sort of result. So that's how many 5s I've seen so far, and some notion of where I am. And then in my loop, what I'm going to do is go around and make a step of progress. So how do I make progress here? Well, the first thing I need to do is look at the item I'm at right now. So I'm going to interrogate x.item. So this is the notation for looking at the item pointed to by X. It's just like when we use an array, we would say A of I, sort of in the array, we're at the ith element. In a linked list, we say through the pointer, look at the item. That's the value it points to. So once I've got that, I can say, well, is it 5 or not? And if it is 5, then I need to increment the result, for example. That does the computation for this step, but then I need to move forward. So how do I move forward? Well, I need to update my x pointer. So I'm going to update the x pointer to have it point to x.next. Once I've done that, then that looks like I'll make progress. How am I going to stop here? Well, I want to stop when I hit null. So whenever x gets to be null, I better not look at x.item, because if I look at x.item when x is null, I'll get a null pointer exception. So I'll do this as long as x is not equal to null. So there's my loop. It's looking pretty good. What do I need to do? I just need to return the result at the end. And I also need to figure out how I'm going to start this guy. So you'll see I'm getting some errors, and the errors are just that the value may not be initialized. So I need to pick initial values. Well, do I need to do anything special at the beginning here? No, I have a good 0 value for this problem, which is I'll just pick the result initially to be 0, and I can then set my node pointer to point to the first node. So the way I write that is I just say this dot first. So now I have x pointing to this dot first, and I will continue through and run. For consistency with my slides, I'm going to edit this a little bit to shrink up the constructor so that my num5s method starts on line 11. And let's just look at what happens as num5 starts to execute. The first important thing to notice is that we invoked num5s with list 1 on line 28. That means that the special variable this is bound to list 1 when we execute the method. Indeed, you can see that list 1 holds the values 5, 11, 5, 5, and when we invoke nums5s, this is pointing to that playground. When we start the method, we first initialize result to 0, then we initialize the pointer variable x to point to the first node, then we start the loop. If x is not null, we look at x.item and increment. Here x is not null. We're pointing to an actual node, so we will go to line 15, check the item, we see that it is a 5, so we'll increment the result, and now on line 16 we move x. So what are we going to do here? Well, we follow x to find the next pointer. It's pointing to this object, so we are going to copy the pointer here back. Sometimes this step is a little fast for people, so let me split it up into 2 parts. What I'm going to do here is on line 16, I'm going to copy x.next into a new variable called y. What is that going to do? It's going to create a new variable that refers to x.next. Then I'm going to copy the value of y into x. What is that going to do? Well, it has the effect of moving x forward. So now x is where y was. Going back to the original code, we have x pointing to the second item. Now, going around the loop, we'll check to see if that item has a 5. In this case, it does not. So we'll simply move on to the next item. Again, we'll check it. We're not null. The item is 5 in this case. So we will increment the result and move on. The way we move on is, of course, to set x to be x.next. And as we keep moving through our list, we'll see another 5. We'll increment the result. And now we're going to set x to be x.next. But note that next here is not a pointer to an object. It is null. And what does that mean? It means I'm going to copy the null value into x. And x is no longer pointing anywhere, so I don't draw it as a pointer. It's instead the value null. And at this point, line 14 will terminate the loop. So we will go on to line 18, and we can return the result. So this is how num5s computes in a loop. Of course, anything I can do in a loop, I can do using a forward recursion. So let me just take the loop in my code and put that in a helper function. And now we'll edit this to turn it into a recursive call. So a couple things to note. One is that I don't need these variables in my starter function because they're only used once. So I can replace them in the method call. So that's just fine. And this will work just fine, does the exact same thing. The other thing to note is that use of this dot in Java is optional. So if there's no other variable with the name that you have on the right-hand side, you can remove this dot and it works just fine. In this case, there's no variable called first, and you can see Java actually colors this blue, indicating that it is indeed a field. If you look at the constructor, you'll note that there I have a parameter that has the same name as the field. As a result, there we write this dot item gets item in the constructor. Note that in this case, this dot is necessary. If I were to remove it, I would end up doing a nonsense thing, which is just assigning a variable to itself. And in Java will give me a warning. So the this dot here is necessary because I have a local variable with the same name as the field. This is very common in constructors, and you'll see in Eclipse that the local variables are brown and the fields are blue. To convert this from a while loop to a recursive function, I'm going to remove the while, replacing it with an if, and removing the update to the iteration variable, and replace that with a recursive call. So what I'm going to do here is say something like this. Where I am moving forward each time I do the call. So we can run this and take a look at what it gives us. In this case, when we call the helper function, our helper will be called first on the first node. So note that when I invoke the helper function, I'm invoking it on the first node of the playground. That will look at the items stored there and potentially increment the result. And once we've done that, we can do a recursive call. And note the recursive call here, we end up with 2 copies of x, 2 copies of result. That's because each recursive call has its own copy of the local variables. And here, the x for the second call is the second item, whereas x for the first call is the first item. This continues out. And you'll know Graphiz gets very creative in drawing these diagrams over time. But it will eventually get to the last method, invocation, where x is not actually a pointer to an object, but instead x is null. At that point, we should have computed our result, and we can simply return the result going back. So we'll return the result here, going back through these methods. So that's a loop and a forward recursion through a linked structure. Before I show you the backward recursive version, though, let's take a step back and look at what's going on. And we'll see that we have choices with linked structures that we didn't actually have in array lists. Here's the code we had for our original loop. We can think of this computation in terms of the state of the variables as the computation proceeds. There's 2 variables in the while loop, x and result, and we can sort of keep track of what they mean at each iteration of the loop. Here I'm showing x's value symbolically, rather than showing it as, a pointer into the memory. I'm just saying, well, it's pointing to the beginning of that list. Here it's pointing at the second element, here it's pointing at the third element, etc. And you can sort of see as I compute here x is the first element, here it's going to the second element, here it's going to the third element, to the fourth element, and finally to nil, which represents the end of the list. And you can see that the result is computed as we go through the list. What's the recursive version doing? Well, it's doing the same thing, of course, but rather than thinking of this in terms of the state of the variables, we think of this in terms of the parameters and the results. So you can see the initial parameters here for each call, and then the value of the result. The initial parameter here for the first call to the helper is pointing to the beginning of the list with result initially 0. We then move on to a recursive call where we're pointing to the second element of the list and the result is initially 1. And we keep going like this all the way till we get to the bottom of the list, where eventually we hit the base case where x is null. There we simply return the result we've accumulated, which is 3, and now we just pass that result all the way back. So you can think about this computation in terms of the function call parameters and the return values. And that's different from the way we think about while loops, where we think about the state of the machine at each iteration. With recursive calls, we think about the parameters and the results. This is the same code for the recursive call, just written slightly differently here. This is a more typical of recursive code. You write the base case and return from there. Then after that, you have the inductive case. And there's something to notice here, which is that I am allowing x to be null when I call this. So if you look at the num5's function, we don't check first to see if it's null. So on the empty list, we'll just immediately call the helper function. So it is the helper function which checks x to see whether it's null or not. This is called a forward recursion with a nullable argument. So the parameter x here is nullable. It may be null. It's sometimes convenient to write code this way. It often gives you shorter code, but sometimes it's not convenient and it's nice to check for nullity before you do a recursive call. It's important, just like it's important to be clear whether you're doing forward or backward recursion, it is important to keep clear whether or not you're working with a nullable argument or a non-nullable argument. And it's important to be consistent in how you do it. So here we're saying the pointer x may be null. Therefore, there's no reason to check it in this starter function. If I do want to check it in the starter function, I end up with subtly different code. I'm going to check if first is null, and if so, I'll return 0. Now, the nums5 function can be called, and the nums5 function may assume that its parameter is not null. What does that mean? It means here I don't have to check for nullity. In fact, I should not check for nullity because I know that x is not null. I may directly use x.item here and increment the result accordingly. But note that when I do a recursive call on x.next, I need to check that x.next is not null before I do the recursive call. And the reason here is that I am assuming that x is not null when I get to that recursive call. So if you look at the computation here, it works very, very similarly. However, in this case, I am going to stop a little bit earlier. I'll hit the base case, not when x is null, but when x.next is null. So here is going to be my base case where x.next is null. I will immediately at this point return. So you'll see this actually does one call less than the nullable version. The nullable version is going to do a call to nil, whereas the non-nullable version will not. So these are two different styles. They're both useful. In general, the nullable style will result in shorter, clearer code, and I encourage you to use it. But you should get comfortable with both of these styles, nullable and non-nullable recursion over linked structures. Returning to the version with the non-nullable argument, we'll now look at the backward variant. So of course, what we do in a backwards variant is simply invert lines 16 and 17. So we're going to swap them around to make it first do the recursive call, then after the recursive call, we'll increment the result. In this case, I am going to have to check for the non-nullity of next before I do the recursive call. And this does create a little bit of complication in the code, but it's fine. What I'm going to do here is use the conditional in the expression language of Java. So I will check to see if x is null or not. If x is null, I'll simply set the result to 0. If x is not null, then I will do the recursive call and set the result to be the result of the recursive call. You can also write this as an if then else. It works both ways. This way is slightly nicer in Java because I'm declaring the result variable exactly once. In any case, what's going to happen after I compute the result on the tail of the list will be to look at this particular element and then add it in. We can watch the code execute over here. We start at line 13 calling the helper function. The helper function starts at line 16 and immediately does a recursive call. So we will immediately do a recursive call, a recursive call, a recursive call. Once we have x.next being null, then we'll initialize the result variable to 0. We then are going to look at the item and see whether or not we have a 5. Indeed, in this case we do. We'll increment the result and then return. That return value will initialize the previous call. So we now have a result of 1 in the previous call. We check to see if there's a 5. Indeed there is. We go up to 2. And now we'll return 2 back. That gets saved in the previous call as the result variable 2. In this case, we don't have an item 5, so we'll skip and we'll simply return 2 again. That will get copied into the result variable of the previous call. And once we're there, we'll look at the x.item, which is indeed at this point 5. So we'll increment the result. And now we're done and we can return. So if you look at the computation, the way it works, we're going through the list and we're just going to stop one iteration earlier. Works just fine. So that is the backward recursion with a non-nullable argument. And again, there it is, forward, backward, forward, backward. And for those of you that don't like this query colon syntax, you can write it out with an if then else as follows. The final variation we'll look at is a backward recursion with a nullable argument. In this case, we're going to simply start our helper function immediately without checking for null. And our helper function now becomes responsible to check for null. So our helper function will check, then do a recursive call on the tail. Note that we're not checking that x.next is not null. We're not checking for nullity of x next. We don't have to. It'll be done in the subsequent call. So let's just watch this execute as well. We're going to start off here. Our first helper function will be on the first item. That's the item with 5. And now in our recursive function, we're immediately checking for nullity. We're not at null yet, so we're going to proceed and on to the next recursive call. So we'll pile up these recursive calls until we get to the end of the list. Note that the end of the list here, we're not going to stop when we get to x.next. We're going to keep going. So we do one more call on null. So the final call here will be where x is null. When we hit null for x, at that point on line 15, we can return 0. And now we're going to start doing the computation as we go back. So we'll return copying 0 into line 16 of the previous call. And then in that code at line 17, we can check x.item. And of course, now we're at the last item of the list. And so it is a 5. And we'll increment the result and return. And we're going to proceed like this over and over again. So note that the result is going to be incremented. Then we return. And it gets copied, the result is copied into the result variable for the previous call. So that's where the previous call gets a result variable, and then we'll check the item and proceed. So that's how we do a backwards recursion with a nullable argument. In this lecture, we've talked about how to go through a linked list, and we've done it 5 different ways. We did it with a loop. Then we did it with a forward recursion and a nullable argument. Then we did a forward recursion and a non-nullable argument. Then we did a backward recursion with a non-nullable argument. And finally, we did a backward recursion with a nullable argument. By learning to code in all 5 styles, you'll become a much stronger programmer, in particular with respect to recursion. Common beginner errors confuse these styles. So when I'm grading exams, when I'm looking at beginner code, I often see students mixing various styles in different branches of their code. If you have a clear idea of what you're doing, I'm going backwards, I'm nullable. If you have those clear ideas, then your code will be clear as well. I've put one more slide in here for those of you that want to play around more. We've learned 2 ways to represent collections. We've done it with arrays and we've done it with linked structures. So to give you practice playing around with functions over both of these things, I've written a playground here that will create an array and a linked list for you for any given string you want to throw at it. When you create a playground here, you'll get both an array and a linked list, and you can write your function in either style and sort of play around with how they work. Next week, we're going to look at functions that change linked lists. These are much harder to understand than these simple functions which access the elements of a linked list. So you really need to get some practice playing with these accessor functions. These are simply looking at the values in the linked list and reading them. So play around with these kinds of loops, try your own functions, and next week we'll do the harder job, which is to look at how you write functions that actually change the structure of a linked list, inserting things, deleting things, reordering things. Accessing linked lists is fun, but mutating them is even more fun.